microphones muted if you're not speaking. There's a few of us with videos on. I think Zoom is more stable without everybody having videos on, or if most people have them off. But it is useful for the speaker to see some people. So if one or two students want to turn videos on, I think that would be useful for Claudio, so he can envisage people watching him rather than just being in a room speaking to his cat or whoever happens to be there. Just a couple of announcements. The web page now includes links to the students' contributed talks. The students can contribute talks of up to 10 minutes. To do this, you have to pre-record it, put it somewhere online, for example, YouTube, and then there's a form to fill in. There's a few people done this so far, and on the web page, you can find a link to them all. And just remind the students, if you should have already heard about this, but there is a competition here. The best talk, as judged by the organizers, will get a prize yet to be decided how, and the opportunity to present your talk live next Thursday, so towards the end of the conference. But it would be great to see more of you putting up little talks online. There's instructions on the webpage to do so. And for those of you who aren't students, you can watch the talk submitted so far. There's links on the webpage. The etiquette for the meeting is that we do encourage questions throughout the talk, but please don't interrupt the speaker yourself. Please either put your hand up, which is a little button in the participants list, or write something into chat, and then one of the moderators, so for example, Piers, myself, or Gunnar, will interrupt the speaker on your behalf at an appropriate moment. And with that, thank you, welcome back, and let's hope we don't have a crash like yesterday. So over to you, Piers.
Okay, thank you, Sam. Good afternoon, everyone. And that's the first thing I wanted to say, is that if we have a crash, just log right back on and we'll keep on going. Hopefully we won't have one today. Let me introduce to you today's speaker. In fact, today's speakers both have in common an interest in aspects of spin physics and also fractionalization. So it gives me great pleasure, actually, to introduce Claudio Castelnovo. Claudio comes from Milan, and that's where he was an undergraduate. He studied for his PhD at Boston University and then returned to Europe in 2006. He was a postdoc at Oxford, and he was a colleague of mine as a lecturer at Royal Holloway, University of London, before joining the Cavendish Laboratory at Cambridge in 2012. His interests span from frustrated magnetism, topological order, all the way across to quantum information. Claudio is particularly well known for his prediction of monopole formation and spin fractionalization in spin ice. This is a prediction that's been borne out in experiment, for which he received the EPS CMD Europhysics Prize in 2012. I should also say that Claudio is a veteran of condensed matter in the city, which he's actually helped organize since 2010. And we're really happy to have him here today to present two talks this week and next. And his first talk today is pedagogical, and it's entitled A Brief Introduction to Quasiparticles in Frustrated Magnets. Let's welcome him with a round of applause. Welcome, Claudio. You can unmute your mic. Over to you, Claudio.
Thank you very much. It's a great pleasure to give this presentation. I forewarn the audience, this is actually the first time that I give a presentation in such setting. So I will do my best to make it as productive, as enjoyable for everyone as I can. But very much in the spirit of condensed matter physics in the city, I do welcome interactions. I appreciate that they will be harder to come by in this format than perhaps in person, but please do put your hands up. I'm very happy to stop and explain things better or clarify. It's difficult for me now not being able to read the audience, whether I'm going too slow or too fast, or whether I'm being clear or not. So if you help me with that, together we can maybe make this presentation the best that it can be. And I thank very much the organizers for this opportunity. It is a little bit perhaps funny to thank the organizer when I'm one of them, but at the same time, I will have to admit and also apologize to all the other organizers. And this time around, I've done very, very little for the organization. They have done a fantastic job putting this together in such exceptional circumstances, and it's so well run. I really owe them a debt of gratitude, and also hope that I can return the favor and some other opportunity and do more of the work when some of them will need to take time doing something else. Without further ado, let me go on to today's presentation. I was offered the possibility to do an introductory and a more specialized talk, and it works very well with what I'm gonna present. So it was a perfect opportunity because on Thursday I will be talking about quantum spin liquids, but in a temperature regime that hasn't been studied very much. And I will try to make the case and convince you that it's actually both interesting and of experimental relevance. But because it hasn't been as thoroughly investigated so far, it does benefit from an introduction to frustrated magnetism, spin liquid, and quasiparticles that is stated in a slightly different way from more standard ones one may find in the literature or in other presentations. And so this introductory talk will be quite spot on, because together with reviewing some of the fundamental concepts in frustrated magnetism, and in particular focus to their quasiparticle excitations, it will allow me to do so in a language that will be a prelude to the talk next Thursday. For this reason, there will be a little bit of an overlap between the two talks. In order to maintain the Thursday one next week self-contained, there will have to be some level of repetition, and I apologize ahead in advance. But it also means that today's presentation can be treated in an accordion manner, in the sense that we don't have to get to the end of it. And that reinforces the statement of please do interrupt if there is something that is not clear. It's more important that we understand together what will be presented. Then getting to the bottom of the slides, I will have the opportunity to end this talk anyway in a coherent manner and adapt the second one accordingly to how far we've gone. Okay, so without further ado, what I plan to do today is, starting at a very introductory level, briefly, a review of what conventional magnetism is and what frustration does to it and how it changes its behavior, introducing a spin liquid regime. And I'll mention briefly what this spin liquid regime is and how we can model and characterize it. And the rest of the talk will essentially be an attempt to give a flavor of what this new regime contains, what type of properties and behaviors we may expect, how do we come to understand them, and in particular, we will focus on quasiparticle excitations, and I'll do so starting with statistical mechanical models that are easier to understand, so at the classical, if you want, level, and two iconic ones, the 6-vertex and 8-vertex model. And they will allow me to introduce concepts such as deconfinement, fractionalization, dynamics of these quasiparticles and the relevant constraints, and entropic interactions. And then I will also start adding a quantum mechanical angle to it by considering more elaborate systems, if you want, or anyway, systems that cannot be diagonalized in the local spin basis. And this will add to the already rich behavior. Fractionalization can extend to the statistics, so you end up with well-known fractional statistics by now. You can have dual quasiparticles, and this will naturally extend the two toy models that I start with at the StatMech level into, or connects them to two also iconic quantum mechanical spin liquids, the Toric code and quantum spin ice. With this presentation, we will naturally come to the energy scales involved and behavior, and also we'll be able to identify this temperature regime that will be the focus of Thursday's presentation, this intermediate temperature regime, and I will be able, in this talk, towards the end of it, to argue why I find it interesting, what kind of physics we may expect to see there, and essentially prelude to the discussion, more specialized discussion we will have about it next Thursday. And I'll come also to some conclusions. As a choice for today's introductory talk, I opted to focus on physics concepts and behaviors, figures, phase diagrams, but as few equations as I could get by. I will try to set a language which will be very useful indeed for Thursday's talk, which will be somewhat general for spin liquids and will not delve into the details of specific Hamiltonians. And I hope this choice is something that you will find useful and will help set up a general framework for the discussion. So as I said, I start from the very basics, and I apologize, this slide is probably overly simplified for many of you, but it's a good way to set the stage. And in order to understand spin liquids, we want to start by contrasting them with what we expect in conventional magnetism. I'm thinking of a spin system, localized spins, with some interaction energy term of strength J. And typical phase diagram we expect is that at temperature large compared to J, the system is in a disordered or paramagnetic phase, and I call it trivial disorder, where I'll quantify what I mean by trivial in a moment. And otherwise, at temperature of the order of J, the system undergoes a phase transition into an ordered state that spontaneously breaks some symmetry in the system. What I mean by the trivial disorder here is simply the statement that this disordered phase exists only for temperature larger than J. And this means that if you want to compute spin-spin correlations, and if you think about their thermodynamic expression, you can expand in T over J, and, J over T, and you can keep the leading order term. So if you've never done that calculation, I'll invite you to do it off the back of the envelope. For Ising spins, it's pretty straightforward to see that the spin-spin correlator from site I and J for Ising spins is essentially the interaction energy term in the Hamiltonian that coupled those two spins divided by temperature. This is only the leading term, but if you are at temperature larger than J, the leading order term is actually pretty good at describing what the system does. And this is what I mean by trivial, in the sense that what we observe in terms of behavior and properties in the system is essentially what we put in terms of Hamiltonian, the Hamiltonian interaction term determining the spin correlations. The moment temperature becomes smaller than J, in these systems, conventionally, you have something catastrophic, a phase transition, and system changes phase altogether. And indeed, much of the focus of understanding magnetic systems over the past nearly a century now has been this phenomenon of symmetry breaking and what's the special behavior that happens at the critical points. That's the most interesting part. The disordered part is solidly understood from very simple principles. What happens if we add frustration in the system? What I mean by frustration is generically a term that represents the inability of the system to minimize all interaction energy terms locally. The canonical example that many of you, if not all, will have seen already is the triangular Ising antiferromagnet. If you take a single triangle as shown here in the figure, if you put two spins and let's say they are Ising so they can be only up or down, well, antiferromagnetism wants them to be up and down, but that means the third spin can be either up or down, resulting in the same amount of energy in the system. And in either cases, you'll have at least, exactly one bond along the triangle being ferromagnetic and therefore frustrated. The result of this frustration is typically to suppress the tendency of the system to order, and TC becomes now much smaller than J. So the phase diagram that we had before gets replaced by a slightly modified one, where the transition temperature to the other phase gets suppressed, and now we allow for the presence in the phase diagram of a phase that is disordered and yet correlated in the sense that temperature is smaller than J. Just to recap here, that's the phase that I indicated the question mark. As you cool temperature, you go from the trivially disordered phase, trivial meaning that the high temperature leading order high temperature expansion term is sufficient to capture the spin correlations, to a regime when this is no longer true. This usually happens via a crossover, not a phase transition. That's the dot that I represent here with tilde1. What happens when the system goes from disorder to correlated disorder, there is typically a change in entropy. And because specific heat is essentially related to the temperature derivative of entropy, you can imagine you'll have some signature of this crossover in the behavior of the heat capacity of the system that typically goes under the name of a Schottky anomaly. But it's a broad peak, it's not a transition. This low temperature yet disordered phase has no longer range order, but has non-trivial correlations because now temperature is smaller than J, and we cannot just trivially rely on high temperature expansion to understand the behavior of the system in terms of spin correlations, for instance. For that reason, it's typically referred to as spin liquid. And one of the challenges in many body condensed matter physics in the last few decades has been actually to try and understand and characterize this spin liquid phases. From this point of view, what I would like to do next is trying to propose and go through with you how we can model these spin liquids. And I will start with the most intuitive case of classical or statistical mechanical systems. And I'll stick for a moment with the nearest neighbor Ising antiferromagnet on the triangular lattice, even though in a couple of slides, I will actually change system for convenience when we move on to talking about excitations. But for the time being, Ising triangular antiferromagnet, if we have spin configurations around triangles, they can be only of two types. You can either have two spins of one type and one different, as shown on the left in this figure, or they can be three spins of the same type. I call them 2-1 type triangles and 3-0 type triangles. You can look at all possible options. These are only two that you can have. And the antiferromagnetic interactions generate an energy different capital delta, which is controlled, of course, by the nearest neighbor interaction J, that splits these two configurations. And you can imagine that at low temperatures, this energy difference will try to favor and therefore project the system onto the 2-1 configurations. This is a general property. As I said earlier, I don't want to discuss much about specific Hamiltonian details. I prefer to actually give a general modeling framework to understand spin liquids. And so this is something that happens generally if we understand many spin liquid phases, where we can take the Hamiltonian and decompose it into a projective part, H capital delta. It's the leading contribution, and it restricts configuration space, yet without causing spontaneous symmetry breaking at temperatures smaller than capital delta. In general, there can be then residual terms in the Hamiltonian. H delta may not be your full Hamiltonian, the original one. And these subleading terms can, at much smaller temperature, result in ordering of the system. And so that's the phase diagram we get at the bottom here, disordered trivial phase, a crossover to a spin liquid, and at much smaller energy scale, the ordering transition. The triangular Ising antiferromagnet is special because this second contribution, H delta, is equal to 0. But we will come later to a more generic discussion when we get to quantum spin liquids, where we will need to take H delta non-zero. This is a general framework that works for many spin liquids, and it will be the class of spin liquids that this talk and Thursday's talk will focus on. It's not at this point clear, at least to me, whether this type of framework is absolutely general. There may be spin liquids where you cannot decompose into a projective classical term and corrections. I simply don't know, because when we can't find one, it doesn't mean that it doesn't exist. It means one would have to think hard on whether there could be a change of basis that would allow us to do this decomposition. But these talks will be actually about systems, and there are many of them where this type of viewpoint holds. So what can we expect given this understanding of the triangular antiferromagnet, Ising antiferromagnet? Well, if we look at the low temperature phase, but above, well, there is no transition in this case because it's exactly only H capital delta, then the system will be made up mostly of 2-1 triangles. And I've drawn patch of the system in this figure here. And every triangle, as I stated earlier, will have precisely one frustrated bond, which is ferromagnetic. It's convenient in terms of understanding the properties of the spin system to actually look at the dual lattice. I don't know if you're familiar, but if you connect the centers of the triangular plaquettes in the triangular lattice, you actually form a honeycomb lattice, which is shown in this figure as dashed lines. And now the bonds of the honeycomb lattice cross precisely one and only one bond on the triangular lattice, and we can put dimers on the honeycomb lattice wherever the corresponding triangular bond is ferromagnetic, is the frustrated one. Because there is one and only one per triangle, that actually results indeed in a dimer constraint. And so we have a 1-to-2 mapping between the Ising configuration and the dimer configuration. The change in language is beneficial in this case, simply because it allows us to understand two key properties of this spin liquid phase in a slightly easier setting. The first one is extensive degeneracy, and the second one is the non-trivial correlations. Both of them are largely beyond the point of this talk, but I will give a flavor about how they come about. Degeneracy, you can convince yourself, or if you have some knowledge about dimer physics, you will know that there are extensively many configurations on the honeycomb lattice. But I will give in a few slides, in a different system, I'll give you a better flavor about how this extensive degeneracy comes about and how you can estimate it. The non-trivial correlations, actually, they're particularly cute if we think about the dimer language. Here I've drawn two vertices of the honeycomb lattice with a dimer in between. In a new interpretation, yet again, another mapping from spins to dimers to fluxes, where I interpret a flux as, a dimer as a flux of unit 2 between sublattice A and sublattice B. I remind you the honeycomb lattice is bipartite. And then the absence of a dimer, I'll interpret it as a flux of unit 1 from sublattice B to sublattice A. The dimer constraint of having one and only one dimer per site is corresponding, therefore, to a divergenceless condition of this mathematical flux that I've introduced as a way to describe these configurations. That suggests, very interestingly, that the spin configuration, which map onto dimer, which map onto flux pattern, are effectively a discretized version of a field that is solenoidal or divergenceless field. And that is suggestive of the fact that if we want to describe them, for instance, by a field theory, what we want to probably pick is a divergenceless field theory. And we are accustomed to this type of field theories from electromagnetism. We know that they're most easily represented as curl of vector potentials with a gauge invariance, and therefore they are actually emergent gauge fields. One thing that this leads to predict is that the field-field correlators will be the same essentially as the discrete flux-flux correlators on the lattice, which will relate therefore to dimer-dimer correlators, with backwards relate to the spin-spin correlators. There are a few geometric factors in these similarities that I wrote at the bottom of the slide, but you can, I hope, believe for the purpose of this discussion that there must be a relation between them. And the flux-flux correlators of a divergenceless field actually have a dipolar nature, and that's very different from typical correlations we expect in a spin system, for instance, especially in the disordered phase, where we expect it to be short-range correlated. So this is actually a flavor of the type of physics you can get in this phase. Unfortunately, we'll have to leave you at that with it. I hope I gave you a tease, and if you're really interested in learning more about these correlations and emergent gauge fields and so-called Coulomb phases, there is a beautiful review by the late Chris Henley in 2010 in Annual Reviews of Condensed Matter that I'd point you towards. There is another reference I'll give later about this topic. But because in this talk, I would like to actually come to discuss specifically the excitations and then quantum mechanical fluctuations, I will have to leave you at that rather than going through the calculation for those dipolar correlations, which actually are quite a nice thing also, but maybe a story for another time. If there are any questions, please raise hand. I'm having a look at the chat and I haven't seen any so far. I also hope that the speed at which I am talking or I'm going forward is all right. And maybe on this front, the organizers can give me a heads up of whether they think I should speed up or slow down.
I think you're doing fine, Claudio. Yeah.
Perfect. Thank you very much.
Raise your hands if you want to ask any questions. Please do.
There's a question of AR is annual review mat. It's a journal. Unfortunately, I only jotted down that as a reference. I didn't really write it down in the talk. Chris Henley, Coulomb phases 2010 and pops up. Yeah, fantastic. Thank you very much.
There's one other question, a hand up from Masaru.
Can I ask a quick question? In the previous slide, you showed that there could be some emergent gauge invariance. And can we show that indeed that this continuum version of this theory is indeed a gauge theory, or can we take the continuum limit of this lattice model?
That is a very good question. So I'm not aware of constructive ways where one can systematically coarse grain the spin system or the dimer model and end up in a control manner with a continuous gauge theory. The best construction I am aware of is one that runs this following way. Follow the intuition towards a gauge field, as I just said. Then you set up a guess for your field theoretic description. That guess allows you to compute spin correlations in the continuum from the field theory. And then you can compare the result from field theory with, say, Monte Carlo simulations of your spin system. And what's noticed in this type of systems, that you find a pretty good agreement at long wavelengths. So that's supportive of the fact that your intuition and the guess of the gauge field theory are correct. But that's the best I can think of. So a constructive way is lacking as far as I know.
Okay. Thank you very much.
We have two other questions on the chat. What determines the direction of the arrows on the dimer, and is the gauge theory a U1 gauge theory?
It's a U1 gauge theory. Yes, the direction is arbitrary in the sense that if I define it the other way around, there is no difference to the correlations.
Okay, and A and B are the two sublattices here.
Yes, sorry, I should have said, yeah. So I pick the direction from A to B. You can say from B to A. So long as it's, so once you tie it to the sublattices, then it's unique across the lattice. So therefore you have no doubts about how to put it down. And wherever, if you chose from B to A, the theory would be essentially the same. It's similar to a Z2 theory change in a nearest neighbor Ising model. It doesn't matter what you define up or down. How this relates to regions?
I don't understand Stephen's question. Stephen, do you want to clarify your question?
Yes, yeah. Stephen, if you want to step in, please do. I assume that you mean like what happens in itinerant electrons, whereas I'm talking about localized ones. That is a good point. I mean, they have a possibility to respond that is different, so it's not immediately obvious that there is a relation. So I think that it would be nice to discuss that, but maybe more, it would take a longer discussion because I don't have an answer off the top of my head. Then it would be worthwhile in the middle. Maybe if you can remember, we can discuss it at the end of the talk.
And Priya Sharma has a question. Priya, ask your question.
Hi, Claudio. It's good to see you. My question was, you can map from the triangular Ising model to the dimer picture. Is it a unique one-way mapping? So can the mapping, is it a bijection? So can you map back only to the Ising model, or you can map back to a bunch of systems that
No,
are...
it's a 2-to-1 mapping, configuration by configuration. So, I mean, essentially, the dimer tells you where there is a ferromagnetic bond.
Mm-hmm.
Of course, it doesn't tell you if it's up, up, or down, down. Therefore,
Sure.
one dimer configuration corresponds to 2 Ising.
Yes.
But other than that, it's 2-to-1 mapping.
So there are no non-triangular Ising models that the dimer model maps back to?
I'm not sure I understand the question. So that one can probably find different mappings to build something else, but for the honeycomb one, I can't think of immediately. Of course, it maps, the honeycomb dimer model maps automatically onto a 3-state Potts model on the honeycomb lattice. Mm-hmm. So you can build many statistical mechanical models.
Yeah, that was my question actually.
Yeah.
Okay, thank you.
You can build others, yes. Any more questions? Perfect. I'm happy with the interaction, so it's very good. So perfect was for the interaction, not that there are no more questions. So since the focus that I wanted to give to this introduction to first magnetism was indeed on the elementary excitations, I will now do a change of setting, simply because in the triangular lattice / dimer model, they are slightly more complicated to discuss. So I want to switch to the square lattice for simplicity, and also because it allows me to tackle in parallel 2 iconic systems with very different yet similar, very different properties, yet very similar in language. And so for that reason, I'm going to shift gear and talk about the square lattice, where the Ising degrees of freedom live on the bonds of the lattice. So I have this top left figure. The dots are my spins, and they can take Ising values plus or minus 1. The square lattice is bipartite, so I can label the sides of the lattice as A or B. And I'm generally look at Ising models in this lattice, and you can always translate them directly into arrow language. We will use it a little later, but I just want to introduce it from the start. Because you have a bipartite lattice and you have variables on the bonds that take values plus or minus 1, you can clearly associate to that plus, say, an arrow from sublattice A to B, a minus is lattice B to A, and so you have now a 1-to-1 mapping between the spins and the arrows. And this gives a flavor of why changing the language makes our life easier. We did a lot of understanding of the triangular Ising antiferromagnet by mapping to dimers and to fluxes. In this case, in this new type of language, in new type of systems, we have a direct mapping between spins and what we could think about as fluxes, and it will turn out indeed that it's quite useful and beneficial. The other reason is that I will talk about, as I said, 2 iconic models, and in the spirit of sticking to concepts rather than equations, I will simply tell you at this stage that I will look at 2 models where the leading energy term, H delta, that acts as projection, takes 2 forms. In one case, I want H delta to favor, out of all possible configurations, the configurations that have around each vertex the sum of the spins to be equal to 0. Because they take values plus or minus 1, this means that you can have 2 pluses and 2 minuses, and they can arrange, say, in this form, and you have 2 possible configurations, or in this form, you have 4 possible configurations for a total of 6, and it's known and therefore as the 6 vertex model. The other model I will do is actually a similar one, but this time I want to impose, well, not impose, I want to discuss a projection term that favors the spins around a vertex to multiply out to +1. Clearly, if you have 2 pluses and 2 minuses, it's good. So you still have the same 6 configurations as before, but you'll also have 4 pluses and 4 minuses that are allowed that were not low energy terms earlier. And so now you end up with an 8 vertex model. And when I talk about elementary excitations in the system, in the spin liquid phase, I want to think about, at this point in time, the excitations that are violations of this projective term H delta. But before we get to this excitations, let's touch base on the properties of the spin liquid phase in the 6 and 8 vertex model, relating them to what we saw a minute ago, or for the triangularizing antiferromagnet in terms of extensive degeneracies and unusual correlations. Again, these are two things that I will touch upon only briefly to move on to excitations, but it's worthwhile actually giving a bit of information for completeness. These models are extensively degenerate. What I mean by that is that they have a finite entropy, or a number of minimal energy configurations that scales exponentially in the volume of the system. While exact calculations are available for these two models, and they're also quite intricate, but there is an interesting estimate that dates back to Pauling when discussing water ice that adapts very straightforwardly to these systems, and I worthwhile going over it in a minute for general knowledge for those of you who may not have seen it before. We have n sites on, so oops, let's not highlight. We have n sites on the lattice, 2 n spins therefore, because they live on the bonds. So in general, a total number of configurations, the size of your Hilbert space, if it's classical, is 2 to the 2n. And then we can observe that for every single star, we have a total of 2 to the 416 configurations, but the minimal energy condition forces them down to a subset thereof. Subset can be either 6 or 8 for the 6 and 8 vertex model. I call this number little n. And so Pauling thought about, in a different context, but thought about the following estimate for the total number of configurations to take the total size of the Hilbert space and then put reduction factors for every vertex you have in the system, assuming they are independent of one another. The reduction factor is n over 16. And of course, you have a total of capital N sites, so it's n over 16 to the n. This is the calculation at the bottom line here. And so if you want the entropy, you just take essentially the log of that. And you clearly see that if n is larger than 4, little n is larger than 4, this results in a number Sn times capital N, where Sn is positive. And that means that you have, therefore, an extensive degeneracy in the system, or if you want, a finite entropy in this phase. There are unusual correlations, and once again, I just give a teaser on this point. The 6 vertex model, we can refer back to what I said earlier. Spins plus or minus 1 map onto fluxes that say a +1 is an arrow from A to B, -1 is an arrow from B to A. And you can immediately think of the 2 vertex condition I had a moment ago, 2 pluses, 2 minuses, being 2 arrows in, 2 arrows out. That's a divergence-less condition that leads us to the same working hypothesis or conjecture that the correct description of this system at long wavelengths is a divergence-less field theory that leads to dipolar correlations. And specifically in the context of 6 vertex models or related systems, I refer now to the paper by Isakov, Meusner and Sondi, if I remember correctly. It's a PRL in 2004. For a specific discussion in this context, beyond Chris Henley's earlier review. The 8 vertex model is different, and in some sense, at a glance, looks trivial, because if you think about the condition of having the product of the spins to be +1 around a vertex, it means that you can flip any 2 spins on the legs of a vertex, and you preserve parity. Essentially, if you have the product of 4 number, if you flip the sign of 2 of them, the parity remains the same. That means that I can take a square plaquette anywhere on the lattice, flip all the spins around them, because they share 2 spins with each vertex adjacent to it. Nothing changes in terms of minimal energy condition. You remain in one of the ground states. Through this, and back of the envelope if you want, you can demonstrate, I'll come to that question in a second, you can demonstrate that the spin-spin correlations is indeed 0 range in this model. Anytime 2-body, anytime you have sigma I, sigma j with I different than j, that vanishes in the thermodynamic average. However, the model is not trivial, even though you seem to have no correlations. You are not just a high temperature disordered phase, you have topological properties that are very interesting. And for these, I'm going to have to leave you with the keyword and maybe the curiosity to look it further if you like. And later on, I'll give a reference to some beautiful work by Alexei Kitaev, which tackles this issue in a quantum context, if you want to read more about it. There was a question whether they are related to integrable Baxter models. Absolutely, yes. The 6-vertex model is integrable, and indeed the entropy was computed exactly by Baxter with transfer matrix techniques. And the 8-vertex model is even simpler. It's also integrable, yes. Okay. Excitations then. What we can do in the ground state of this system, so I drew here a patch, and if I've not made any mistakes, this is an 8-vertex model configuration. Around every vertex, you'll have an even number of minuses. A spin flip here, take the spin circled in yellow, will create 2 vertices that no longer fit in the low energy state. They will have now a product of spins around them that is -1. Generally, we think of a spin flip in a magnet as being the lowest energy excitation. However, in this case, there is something special that happens, because you notice immediately that if you look at the neighborhood of one of these 2 excitations and you flip a spin there, say the one circled in yellow now, once you do that, you heal or you send the intervening vertex back to its lowest energy state, and now you introduce a defect in the site neighboring it. What you have done is that you moved apart the 2 constituents of the initial spin flip. And so the elementary excitation of the system is actually not a single spin flip, but half of it, in a sense. It gets decomposed because this process can continue, and trivially, there is no energy whatsoever holding these 2 defective vertices together. So I can take this star, this site, and sorry, this spin and flip it, or this one and flip it, etc. And you end up separating them at will. The elementary excitations of the system are these single defective sites, even though they are not local in the spin language. If you wanted to introduce one single such defect, you will have to flip spins along a chain all the way out to infinity. But energetically, these are deconfined, and therefore they are the elementary excitations. This is an instance simple to understand in a classical setting, but it's an instance of fractionalization that Pierce was referring to in his introduction earlier on. So if we think about modeling this from a point of view of behavior of the excitations in this spin liquid phase, what we have is a zero-range correlated background that allows pair creation and annihilation of defects, and the defects can hop wherever across the lattice. So essentially, they are random walkers, and we can expect diffusion properties. The situation is slightly different in the 6-vertex model. Remember, the spins underlying it have non-trivial correlations. That's also already a telltale, but this translates also in non-trivial properties of the excitations. We can do the same, take a patch of the system. Now I have changed the spins so that every vertex is 2 plus 2 minus. Flip a spin, say the one circled in yellow, and you end up with 2 vertices where the sum of the spins around the vertices is not 0, as it would have been in lowest energy, but now it's a value plus or minus 1. You can repeat the process as before. We can select a neighboring spin with a caveat, but let's say we take the one circled in yellow right now, we flip it, and again, we put the intervening vertex back to 2 in, 2 out, or 2 plus 2 minus lowest energy state, and we move the defect to another site. There is one subtlety with respect to what we did before, is that we cannot do it everywhere. If we go back for a moment, think about the spin above this defect, this -1. I hope you can see my mouse. And if you flip that one, clearly you would do something very different to the system, because the intervening vertex now would be a 4 plus, which is again an excitation. So the spins, subsequent spin flips in the 6-vertex model can separate these excitations, but only if you keep flipping a chain of plus minus alternating sign of spins. If you go back, we started with a minus, then a plus here, minus, plus, minus, continue. And if you look at along the yellow line, it's a sequence of plus minus signs that got flipped to minus, plus, minus, plus going along. Again, however, they are deconfined, so there's no energy term holding them together. And we have this understanding of excitations in the 6-vertex model as being a gas of particles subject to some constraints. And they create and annihilate in pairs. As one may have thought, thinking about the understanding of the triangular lattice antiferromagnet in terms of fluxes, maybe it's worthwhile looking at what happens to these excitations in the gauge flux representation. And indeed, this becomes quite a powerful tool to make better sense of this constrained motion of the particles and their interplay with the vacuum. In this case, I'm represented the full spin configuration I had before in arrows. It's a one-to-one correspondence, as I said earlier. So I can repeat the exact process I did before. At this point in time, we're in the ground state. So every vertex is 2 arrows in, 2 arrows out. And I pick the spin that I selected before, circled in yellow. I flip it, which means I reverse the arrow. And you see that I create 2 defects. But now I can label the defects differently, because one defect says 3 arrows in, 1 out, and the other is 3 arrows out, 1 in. So we see that if we think of the arrows as carrying flux, the defects now have assumed a role of gauge charges in the flux language, because they are sources and sinks of the flux. And the gauge charge is actually conserved as we move it around. Again, flip the spin at the bottom. It moves here. This one goes back to the ground state, and this is still a 3 out. So it's still, say, a source of gauge field. And we can keep going and separate them at will. The condition that you can do this only along alternating sign plus minus in the Ising language translates into the condition that you can only do it. Oops, what I wanted to do is this. You can only do it along oriented paths of arrows. And you can see it particularly well in the cyan arrows right now after you've reversed them. There is a close interplay, therefore, because the defects, their motion is constrained by the underlying spin configuration, vice versa. As the defects move, they change the underlying spins. More importantly, another aspect that we can realize is that these are lattice gas of gauge charges, where the spins form a field that source emanates or sinks on these charges. And therefore, we expect generally to have some kind of Coulomb interaction being mediated by the spins between these charges. And I want to open a parenthesis here because it's cute to understand what we mean by this Coulomb interaction. I stress there are no energy terms between the defects. So generally speaking, if you don't have energy and you have quasiparticle excitations in a lattice, you expect them to be distributed across the lattice randomly with respect to each other's position. On the other hand, if you actually look at these systems and you compute the probability of having 2, say, oppositely charged defects at some distance r from one another, you realize that actually this is not a uniform distribution, but rather is the exponential of a Coulomb potential, some function that takes the form of a Coulomb potential in d dimensions as a function of distance r. If we looked at this probability distribution face value without knowing where it's coming from, what we would interpret is that there is an energy term in this system that tries to push these 2 particles together. And this energy would be the negative, so it's attractive, of the Coulomb interaction multiplied by temperature, what we refer to as an entropic Coulomb interaction. And the reason why I expressed everything here in terms of d dimensions, generally speaking, is because I wanted to show a result, but I only had it for d equal 3, whereas we've been talking about a moment ago for d equal 2. So I wanted to leave it generally. In d equal 3, the Coulomb interaction is, of course, 1 over r. And this plot shows indeed Monte Carlo simulations that compute this probability. It's the log of this probability on the vertical axis and the 1/r inverse separation on the horizontal axis. And you see that at large distances on the left-hand side, you have a pretty good linear behavior that allows you to obtain the strength of this Coulombic attraction that is entirely mediated by the spins. It's entirely entropic origin. There is a question. Let me have a look 1 second. XXZ model, we know that the fractions carry spin 1/2. You're talking about spin in the sense of statistics, I presume. At this point in time, I'm discussing purely a classical model. When you add quantum fluctuation, there is an interesting question about statistics. It's not immediately set of which one is correct in terms of whether they should be spin 1 or bosons or fermions. 6-vertex model on the cubic in D equal 3, you would have to use a diamond lattice that is 4-fold coordinated, and therefore the language translates entirely over. You can do a cubic lattice, but then you have the 3 in, 3 out vertices. The physics is very much the same, but it wouldn't be a 6-vertex model because you don't have only 6. What determines whether a 6-vertex or 8-vertex model, if you know the microscopic details of the model, you can look at what are the relevant energy terms in the Hamiltonian and which one acts as a projector term to leading order. Alternatively, you can look at the physics or the behavior of the system somewhat blindly, because in one case, you have this emergent gauge symmetry that leads to dipolar correlations that has a very remarked signature in the structure factor. So if you say you had a material and you wanted to know this, Coulomb phases would have to have very distinctive features in neutron scattering, whereas the 8-vertex model is in some sense pathologically simple because it does look like a paramagnet on all accounts until you actually see its topological properties, other than the finite temperature window that I mentioned earlier, which will be the subject of next Thursday's talk. And there I'll give you perhaps new ideas of how to get interesting behavior out of something as simple as a Toric code. But that will have to wait until next Thursday. Okay, perfect. Very good. So we have question for the organizers. Is it okay if I take the full hour, or should we want me to stop earlier?
You have an hour and a half, including questions. So because there's already been some questions, it's fine even to go slightly beyond the hour.
Excellent, splendid. So then I have no worries. At low temperature in these systems, as I've argued so far, the dynamics of these excitations from a purely classical point of view can be summarized as follows. At temperature smaller than this projective energy scale, the defects will be sparse. So we're thinking about a sparse gas of these particles that can, in the 8-vertex model, random walk generically on the lattice with pair creation and annihilation events. These are often known as reaction diffusion type processes. It's one chunk of literature that relates closely to these systems, for instance. In the 6-vertex model, the language is slightly different because now the motion is constrained. So it leads to some peculiar anomalies that wouldn't be accounted by a standard random walk. And on top of that, there are these entropic Coulomb interactions. And at the level of classical dynamics and of these StatMech models, there is actually quite a bit of literature already that makes this topic rather interesting and dates back all the way from Toussaint and company and Ginsburg and Wilczek, who looked at random walk and the role of Coulomb interactions. And then more specifically relating to frustrated models, I could refer you to work by Rishkin in 2005, 2013, and then also work done by myself and collaborators in 2010 and 19. These are not by any means an extensive nor comprehensive list of references, but if people are interested, that could be something to look into. Yes, so if you have more than one pair of excitations, then they act as gauge charges to all effects, which means that the particles with the same gauge charge cannot annihilate and repel one another. Whereas in the 8-vertex model, where there is no notion of a gauge charge, the charges act in the same way as if you want gravity with respect to mass. They don't have interactions, but they can always annihilate one another. It doesn't matter which one. So they're only one type, essentially. Okay, these are pointers of what one could look forward to in the context of a classical language, but really what I would like to switch gear now for the remaining part of the talk, and I don't have too much to cover, is adding quantum fluctuations and looking at what happens when we turn these spin liquid phases towards quantum. And in the same spirit as the whole of the talk, I won't do technical specific examples of Hamiltonians, but I'll stick to the general framework. We already said earlier that a general framework I'm interested in for spin liquids is one where the Hamiltonian can be decomposed of a projective term, which is classical and reduces the Hilbert space in its in the basis in which is diagonal, and there were corrections that so far we have essentially ignored, which is I labeled that H sub little delta. Generally speaking, these corrections can take different forms, and if we think specifically about defects and excitations in this system, we could loosely classify them as defect interactions, which are still in diagonal in the basis of the defects, and some kinetic terms, non-diagonal ones. So defect hopping, I call them here. I will not discuss the diagonal interacting parts for simplicity. They, of course, can be present and they would change the physics of the system. But what I want to really focus on is the hopping part, because that's the one that will now make the system quantum by not commuting not generically commuting with the projective term. If we turn on this hopping, let's call it strength little t. Generally, we expect it to be smaller than delta. If it's larger, probably it would spoil the spin liquid picture altogether. We still want that projection that sends us from a trivial disordered state to a disordered but correlated setup. When we turn it on in that context, it can lead to two effects. Straightforwardly, to first order, we can expect defect dynamics. If we have a defect somewhere, T will give it some dispersion in a tight binding sense. But also, even if we don't have defects, we expect such kinetic contribution to act perturbatively, because we know that we can create defects from the vacuum and then annihilate them. And so you can imagine the following process represented in the figure on the right here, where you pop two particles virtually out of the vacuum at some energy cost capital delta, and then you walk one of them around some finite area until it annihilates its partner again. This process will come with a perturbative energy term, which I call delta bar, which is essentially controlled by the hopping T with a suppression factor due to the fact that it's a virtual process, T over capital delta, to the number of steps that are done at high energy, which say if you're going around a square plaquette, it's 3 steps you do at high energy, the fourth one comes down, so it would be T times T over capital delta to the power 3. This ring exchange is now able, as an energy scale, to act directly on the ground state, or in general, act on states while preserving the position of the quasiparticles. It just essentially creates superpositions of the spin background. Because it's a perturbative term, it's generally much smaller than T, and so the energy axis that we are looking at for these systems is one where there's the projective energy scale capital delta being the dominant one, we have T somewhere below it, then we have a large gap all the way to delta bar, and below which, and then, well, we have the very low temperature regime. And if we think low energy regime, and if we think about these axes as being temperature instead, what we expect is that above capital delta, it's a disordered paramagnet, temperature wins over everything. In the temperature window between T and delta, what we expect essentially is a classical spin liquid. Temperature will be enough to disrupt all quantum dynamics and coherences, but is still weak compared to the excitation. So we have done this crossover into the classical spin liquids that we have been discussing so far. Then let me skip ahead. If we go all the way down to temperatures below delta bar, that's what we usually think about quantum spin liquid. And that has been the focus of attention all the way down and typically at zero temperature to understand quantum spin liquid behavior in theory, and then also trying to look for experimental realizations. But in the models that I've introduced in this talk and the arguments that I've been presenting, there is an interesting, what I would argue, an interesting intermediate temperature regime between delta bar and T, which is fairly broad because we expect delta bar to be much smaller than T, where the behavior is kind of mixed. From a point of view of energy level, what do we expect as a function of little t can be summarized in this sketch, my poor artistic abilities, but sort of sketch that I have at the bottom left. The vertical axis is the energy levels of the system. As t equals 0, we have the ground state, and then the first excited state produces 2 excitations, so it's cost 2 delta, a pair of them. And these are just discrete energy levels. When we turn on little t, what can happen is that the 2 defect sector can acquire a dispersion because of the defects, tight binding, and therefore it's controlled by t, little t. And the 0 defect sector, little t directly cannot act, but there is delta bar and it acquires a dispersion and therefore a quantum superposition of what's typically taken as the ground state of a quantum spin liquid, which is controlled by delta bar. What I would argue, however, is that the intermediate regime has quite some interest because it's a behavior that is in between classical and quantum physics. If we think about, we are below t, so the defects in delta, the excitations we've been talking about so far, are hopping coherently, but you are neglecting any coherences coming from delta bar, or at least you are justified to propose to neglect them. So it's sitting in between classical and quantum behavior. It may well be, it is in fact the highest temperature where one can perhaps observe precursor quantum spin liquid behavior. The ultimate phase that we are targeting, if you want, is the quantum spin liquid down there that has properties that we're fascinated by, from topological order, fractionalization, to possible topological quantum computing, outlook, etc. But in order to achieve it experimentally, that's a big challenge. And in order to screen materials and candidate compounds, it would be quite good to have preliminary indications of this behavior that live at higher temperatures that are easier to access. So from this point of view, there's an experimental angle that makes this intermediate regime of interest. But I would also say that it's interesting in its own right, because the underlying spins that are in some sense incoherent act as a self-generated or emergent disorder with respect to the coherent hopping of the defect motion. And this gives rise to some rather interesting feedback mechanism and localization effects that will be the subject of Thursday's talk. A general framework for this intermediate regime is still lacking, but there are some interesting case studies. And these are essentially the 4 papers that are gradually becoming a coherent picture, even though they were individual interesting questions that we tackled in my group in recent years, and that will form the body of the talk on Thursday. Or how to identify whether or not a compound is frustrated. The typical signature that one looks at is, say, you can look at Curie-Weiss susceptibility behavior at high temperature to find for instance, to find the typical strength of the interaction in your system, so the magnitude of J. And then you look at the heat capacity or other indicators to show that the phase transition or if there is a phase transition, it happens at temperatures much smaller than J, or there is no observed phase transition down to the lowest temperature that one can access. That's the typical indicator that one can use numerically or analytically, but most typically experimentally to suggest the presence of frustration. Indeed, a quantifier of frustration is the ratio between TC, the TC observed, and the interaction energy scale. Self-generated disorder, I can elaborate. I have a couple more slides, so bear with me. I'll explain it. There are two types, and they're very interesting. And then Thursday, they will be studied thoroughly. But bear with me, I'll come back to that. Delta bar to the amount of entanglement in the ground state. Yes, so delta bar is exactly what causes the entanglement in the ground state. One of the difficulties in answering the question comes from the fact that quantifying the range of entanglement or the amount of entanglement at finite temperature is somewhat delicate, and it's not immediately obvious how to accomplish that, even in theoretical models. But the answer is positive, even though I don't know how to quantify it. If you have delta bar and zero temperature, you create an entangled superposition of the ground state, which is the typical extensive entanglement of a quantum spin liquid. If you turn on temperature, you fight against it. And when temperature is much larger than delta bar, you just have an incoherent, and therefore a classical ensemble of spin configurations rather than an entangled state. Okay. And that's it. Okay. So I have 6 more slides. Just wanted to make sure that I remember them correctly. That would put a bit. Wait 1 sec. Isn't the ring exchange interaction present in the? Yes. That's a very good point. The last question. The division into hopping and delta bar is a little bit of a chicken and egg question, in the sense that once you have defects can go to somewhere, go around the loop and go back. And that essentially is equivalent to go there and back plus doing a ring exchange. Therefore, the defects themselves will implement a ring exchange update. And so it's not immediately obvious how to distinguish them. So in a completely formal way. That's absolutely correct. That's one of the reasons that makes this intermediate temperature regime somewhat difficult to study on rigorous footing. On Thursday, I will present results that are specific for toy models where we can do the calculation, but I think a general framework and an answer to your question on how this is done is in the process of being formulated. But it is indeed difficult to split them. The clear-cut case is when you don't have any more excitation, then you only have delta bar. Then it's clear-cut. Okay. So organizers, can I still keep going with the last 6 slides? Is that all right? You're still muted, Piers.
Yeah, Piers, you're still muted, but from my point of view, yes, go on. There's still time. There's 25 minutes, including questions, so there's still time.
Yeah, carry on.
Perfect, very good.
Please stop the questions, no problem.
Yeah, and then if there are questions, I'll stop and continue with the questions, so there's no problem at all. These are the slides that could have been either here or on Thursday or a bit of both, so I'm not too worried wherever I end up. But there are only 6 and they'll be relatively quick. I just wanted to give a bit more meat because I've given, at this point, if you want, a flavor of what happens in quantum spin liquid language, but without giving you any equations is perhaps a little bit too brutal. So let's actually look at what happens when you take the 8 vertex model and you make it quantum by adding dynamics to the excitations, which in this case is as simple in a language as adding a transverse field. And we'll see that what we get is indeed the toric coordinate field, hence the relation that I mentioned in the outline of the talk. So this is the notation I use. I, J are the sites or the spins. S, are the bonds of the lattice or the spins. Labels. S is the sites or vertices, and P are plaquettes. Just to remind you, we have used them already, but it's always good to make sure we're on the same pace. We have a projective Hamiltonian term, H capital delta, that wants to put the parity to be positive for every vertex in the sigma Z language. So this is what I'm going to write: sum over sigma of the product of sigma I Z around the plaquette, around the star. And then I put a transverse term that allows them to hop, and that's simply a transverse field of strength little t. Delta bar in this case is the simplest perturbative process, which is actually flipping 4 spins around the plaquette, and therefore it will be the sum over plaquettes of the product of sigma I x around the plaquette. And if it's perturbative in t over delta, then this delta bar is t to the 4th power over delta cube. If we take ht away out of the picture for a moment, H delta and H delta bar actually form a very well-known system, which is, goes under the name of the Toric code. And one of the seminal references is still one of the best ones I would recommend people to look at if they wanted to, is an Annals of Physics, sorry, I forgot to put it there, by Kitaev in 2003. The work was actually done in 1996, I think, but he considered it too simple to be worth publishing until people forced him to, recommended him to put it out somewhere. It's a beautiful piece of work. And the beauty in this case is that if we look at H delta, we have our standard projective term, the excitation. So it favors the product or the parity to be 1, and excitations are when this becomes -1. H delta bar favors now the parity of the X basis of the spins to be +1 around a plaquette. Usually, because one is in the X and one in the Z basis, we would think about difficulties studying them together. But in this special case, they actually commute. You can check that they share 0 or 2 spins, irrespective of which star or plaquette you take. The fact that they commute, it means that you can simultaneously minimize them or satisfy them. And therefore, you can simultaneously talk about the 2 defects without any problem. So that means that your elementary excitations in the systems take 2 forms: a star defect, these are the parity that is -1 around a star in the sigma Z basis, and that costs energy capital delta, or they can be plaquette defects. They exist simultaneously in the system, and these are the parity of the sigma X components around the plaquette being -1, and they cost delta bar. These are trivial excitations to some extent. They're bosons, point-like. They can move wherever in the lattice if you want to move them. But they are actually special. This relates back to the topological properties that I really didn't discuss about this system. And they are special because they have neutral semiotic statistics. What this means is that if you have a state that I represented here pictorially with a star defect S and a plaquette defect P, if you take S and move it around P and come back to S, to its original place, you end up with a minus sign in the wave function. If we look at the phase diagram of this system and the temperature range of interest between delta bar and T, what we end up, therefore, is star defects that are sparse and hop coherently because temperature is much smaller than their energy scale, whereas the plaquette defects are thermally populated and dense and incoherent because their temperature is much larger or generally larger than their energy scale. So the type of picture that we get to answer one of the questions of what type of self-generated disorder you can have is that in this intermediate regime, we probably want to think about the plaquette defects as being some incoherent superposition, which is essentially an ensemble average, with coherent star defects hopping around the lattice that are sparse. Because the plaquette defects have a semiotic statistics with respect to the stars, it means that they act as pi fluxes with respect to the star defects if we assume that star defects have some kind of charge to them. So we have a tight binding model of charges in a random pi flux background. This has been studied before in other contexts. It leads indeed to Anderson localization. And so you see that the self-generated disorder is this pi fluxes lying about. Because we started with a system that has no disorder, had no disorder to begin with. But it's simply the fact that in the emergent picture of star and plaquette defects, the plaquette defects act as disorder for the star motion around. And if the star motion is coherent and the plaquette one is just a stochastic ensemble average, this is the picture you end up with. More importantly than the dynamics and Anderson localization that have been studied before, there are some very interesting feedback mechanism in the thermodynamics properties and some phase separation phenomena that are due to the mutual statistics that I think are very interesting. But I will leave you with that teaser, and that's going to be the topic discussed on Thursday. Yep.
Claudio, can I ask a quick question?
Yep.
Yep. So normally we associate localization with quenched disorder, random disorder. Sorry, with frozen random disorder, whereas here it's annealed disorder. So does that make a difference?
Yes. It's a matter of timescales. Mm-hmm. So this is going to be really the topic of Thursday, but I give 1 minute answer here, and I will do a better job on Thursday. The point is that you can think about energy scales in the system as, if you want, as inverse relaxation times. I mean, if typically if you have a tight binding model with amplitude t, you expect the time scale to be essentially 1/t, characteristic time scale to the system. Mm-hmm. So, and in this model per se, we actually fine-tuned to have no dynamics for the fluxes whatsoever, but there would be stochastic dynamics. Mm-hmm. In general system, there would be a T prime that would correspond to the hopping of fluxes or plaquettes. But we expect T prime to lie somewhere below delta bar. Mm-hmm. In order to preserve the toric code picture, otherwise it would be spoiled. So if T prime exists and is below delta bar, its corresponding timescale 1/T prime is large compared to 1/T. So the picture of Anderson localization holds on timescales where one can use a Born-Oppenheimer type approximation, and the fluxes are essentially static on the response timescales of the star defects.
But doesn't Anderson localization involve very large loops? And therefore you have to look at the timescales for the large loops, not just single hops from site to site.
Indeed, yes. Okay. So it's a matter of like how separated, at that point it becomes a matter of how separated these scales are. Mm. But Anderson localization is, Anderson localization with pi fluxes is particularly efficient.
I see.
Okay. The localization length on which the wave function decays into a random flux region is of the order of the lattice spacing, as a matter of fact.
I see. Okay.
And I'll show results on Thursday about that. Yeah. So I'm sorry that it's not a complete answer, but I will have slides and results about this to talk about on Thursday. And so if it's not complete, my answer is not completely clear, please carry it on. So disorder quench as compared to annealed, I guess that was the same as your question. So any further elaboration, I would defer to Thursday. But it is indeed a very important point, and the picture of Anderson localization and disorder is something that has been made within a certain time scales and length scales, beyond which the motion of the pi fluxes themselves may become important. As a factor of fact, the motion of the pi fluxes is what leads to this thermodynamics response that it's what I'm even more excited about, and then I'll be the topic on Thursday. Before closing, I wanted to draw the parallel of what happens for the 6 vertex model in the quantum language, because it leads to yet another understanding of this self-generated disorder. So same language as before, but now the projective energy term wants the sum of the spins to be 0, 2 plus 2 minus. So the Hamiltonian typically that you put for that is the square of the magnetization of a star. The hopping term is the same as before. You just put a transverse field, sigma ix. This will allow the defects in capital delta to hop around. But now if we look at the transverse term, sorry, the perturbative term, we have to be subtle, because if you remember, you cannot flip any chain of spins, you have to flip alternating signs only. So it takes a slightly different form than what we had before. It's gonna be now like a sigma plus, sigma minus, sigma plus, sigma minus around the 1, 2, 3 bonds surrounding plaquette P plus Hermitian conjugate. So it's a small difference, important for the properties of the system. But the energy scale delta bar is of the same order, t to the 4th power over delta cube. Once again, if we ignore the hopping term, we actually end up with a system that has been studied before, most typically in 3 dimensions in the diamond lattice, but many of the arguments hold. And I refer the reader to the beautiful work by Hermele and collaborators in 2004. And this system goes under the name of quantum, in this case, square spin ice. Once again, if we review what the different terms do, H delta favors the sum of the spins around a vertex to be 0. H delta bar favors plaquettes that can flip because they can acquire kinetic energy. And these are plaquettes where the sigma z components of the spins are of the type plus minus plus minus. Unfortunately, these 2 terms now are not commuting anymore. And so you cannot simultaneously satisfy them. And this that does not allow us to do as much of an analytical understanding as it's possible in the Toric code case. What we see in this case is that if we look at the elementary excitations, the projective ones are still viable. Oops, let me just go back for a second. So there's a question about the 8th vertex. So delta bar here, again, we are flipping 4 spins around the plaquette, but if you flip 1, you create 2 defects that cost energy roughly delta, and then you flip 1, 2, you separate them, and then you flip the 4th one, and they annihilate. So that gives a delta bar, which is t to the 4th over delta cube. And I hope that's perfect.
Okay.
Or actually,
Claudio, I think maybe it would be a good time to switch to questions.
Yeah. I just want to say, in this case, you have an emergent quantum electrodynamics where the dual charges are not as easily identified, but they can take the excitations that emerge in this case are either the dual charges in QED or photons. And so the intermediate regime is a lot harder to understand. And one of the best things as a working assumption that one can do is to treat the underlying spin configurations as entirely incoherent, which may be a bit too brutal an assumption, but that means that your particles that are hopping across are hopping on a network rather than on a full lattice. And in this case, the emergent or self-generated disorder is actually a configurational one. If there are questions, I'll come back to that slide. There is one question pending, but let me do the conclusions and I come to the question. So I hope I gave a bit of a flavor of what kind of physics frustration can bring about in magnetic systems, and opening this window into unusual and interesting spin liquid phases. And through a couple of specific examples, we've seen the power of effective modeling and to making sense of this spin liquid regime, and in particular the quasiparticle excitations. We've seen some of the key points in classical and quantum cases, and I gave you a tease about this intermediate temperature regime, which will be the subject of the next talk on Thursday next week. I've seen a few questions popping up, but I thank you all for your attention firstly, and come to the questions immediately.
Let's unmute our mic and give Claudio a great round of applause.
Thank you very much. Okay, so does the 6 vertex model share some similarities with spin ice on a checkerboard lattice? Oh, yes, absolutely. It's actually the same thing. So they are one and the same model.